In this video, I'll try to explain you the generalized energy for closed orbits in central force field when any object or particle is moving in central force field. So this kind of questions are frequently asking in many competitive exams like JAM, NET and GATE, and like many other exams also. So that is why I felt to discuss this topic in this video. So, and also at the end of this video, I will try to convincing you that for the closed orbits in central force field, so we can have an energy formula which is more generalized, so which can be applicable for both elliptical orbits or for the circular orbits. So in fact, this circular orbit is a special case of the elliptical orbits that I am going to explain you today. So by doing a very small derivation, okay, assume that this is the elliptical orbit, and in this elliptical orbit you know that this is the semi-major axis and this is semi-minor axis. So I now consider there are two positions for the planet now. So one position is here and the other position is this much. Okay, this is the second position and this is the first position for the planet when it is moving around the sun in the elliptical orbit. Now, what is the total energy of a planet, whether it is at this position or in the other position, anywhere in the orbit? The total energy have to be same. Okay, so that is very important to understand here. So let me write the total energy E as the potential energy plus the kinetic energy. So potential energy of a planet when it is in the gravitational field can be written as, there is a negative sign, and G M divided by this R. I tell you what are all these notations, they will carry their usual meaning. And the kinetic energy is half mv square. Okay, so this G is a universal gravitational constant, and this m is the mass of the sun, and this small letter m is the mass of the planet which is moving around the sun, and this is as usually the radial distance measured from sun to the planet, and this is half mv square, where m is mass and v is the velocity of the planet. Alright, so now let me write the energy of the planet when it is here and here. Okay, so those two energies of the planets at different positions anywhere in the orbit must be same. So because wherever the planet goes, in all the cases, in all the points in the orbit, total energy must be same. But the only thing is, because the distance of the planet from the sun is changing when it is moving, the kinetic energy and the potential energy is going to changing. Okay, but they are changing in such a way that the total energy is always constant. That is what the core concept here. Now assume that the planet is here, so it is moving in this direction, anti-clockwise direction. So at this point, assume that it is having a tangential velocity. Let me call the tangential velocity as v1. So here at this position, the tangential velocity, let me call it as v2. So now what is the total energy at this position and this position? Alright, so that total energy is given by, so first let me write the kinetic energy. Kinetic energy is half mv1 square. Potential energy at this point is as usually it is negative sign. Potential energy is always negative, minus Gm divided by the distance square. Here the distance is a. So like we write, it is a square. So this is what the total energy of the planet, and this must be equal to the total energy over here at this position. So that is why let me write, this is also equal to half v2 square, where v2 is the velocity at this point, minus Gm divided by the b square, because the distance here is equal to semi-minor axis. That is why it is b square. This is also the energy for, or the expression for the total energy. Now, the one more thing that we have to understand here in the motion of the planets around the sun, in whichever the orbit, and it is very clear that this gravitational force between sun and planet is actually the central force, which means if this is the sun and this is the planet, the central force means the gravitational force of attraction between them is always acting along the line joining those two objects. I mean, from sun to the planet. Okay, and not only that, this the magnitude of this central force. Okay, this gravitational force is purely depends on, or it is exclusively depends on the distance between the sun to planet. So that is why it is called as central force. We have discussed already central force in our previous videos, so let me not go much into the central forces. So in central forces, you know that the torque acting on the moving particle, so here the moving particle is the planet. So torque acting on the planet is completely zero, because what is torque? Torque is force into perpendicular distance, or it is the cross product of distance and the force. That is what actually the torque. So which can be written as this R, F and sin theta. So what is this theta here? Theta is the angle between this R and F, because it is the cross product of R and F. So therefore here, if this is the planet and this is the sun and this is the planet, the force between this sun and planet, since it is acting exclusively along the line joining the two objects, either this theta, I mean the angle between this R and F, either it is going to be 0 degree or it will be 180 degree. In both of these cases, when you substitute theta is equal to 0 here or theta is equal to 180 degree over here, torque must be 0. So when the torque acting on the object is 0, it is very clear from the Newton's second law of motion in rotational motion that torque can be defined as dl by dt. So where the change in angular momentum with respect to time will give us the torque, and I am telling you that in the central force field, torque acting on the moving object is always 0. So I will put this torque is equal to 0, therefore dl by dt is 0, which means angular momentum of the planet or any object moving in the central force field or in the gravitational force field is always equal to constant. So angular momentum is not going to change. For that, I put the condition that the angular momentum of the planet at this position and the angular momentum of the planet at this position must be same. They are not going to change at all, because we know that torque is 0 and hence the angular momentum anywhere in the orbit is constant. So that is why, so assume that the angular momentum is here also angular momentum is here, and angular momentum is given by m, v and the distance. The distance here at this position is a, and the velocity at this position for the planet is v1. So this must be equal to m, v2 and v. Okay, so this linear momentum times the distance will give us the angular momentum usually. That is why I am writing, so m into v1 is the linear momentum multiplied by the distance a. So angular momentum at this position is equal to angular momentum at this position. So you can cancel m on both the sides of this equation. So you will get this v1 by v2 is equal to, what do you call this, b by a, or you can express either v1 or v2. Okay, so I take v2 itself. So v2 is comes out to be v1 times the a by b. So we got this is an important equation which will be substituted in future steps, which will be requiring to derive generalized formula. For that, we got the velocity at this position v2 is equal to velocity at this position of the same planet multiplied by this a by b, where a and b you know that. So this equation number 1 will be substituted in this steps as we have written here. So derivation is not necessary, so it is simply waste of time. So you can take a screenshot of this derivation, so that we will be getting the final formula over here. So but let me simply explain this, what is what. So this is the total energy of the planet at this position, and this is the total energy of the planet over here. Because the total energy is same, I have equated them. So and finally go on simplifying this just by substituting this V2 as V1 into A by B over here. So we are go on simplifying, and finally we get this equation E is equal to minus GMM divided by B plus A. So here it is very clear that this total energy of the planet comes out to be negative. That is obvious because the motion of the planet is restricted around the sun itself, it cannot escape out. So this negative sign represents that this much of energy is shortage for the planet, just go out of the sun's control. Okay, so that is why to represent that shortage there is a negative sign. So let me discuss how you can get the circular orbits. So I told you in the beginning that the circular orbits are nothing but the special case of elliptical orbit. Let me see how. Yeah, so finally we got the expression for energy of this okay, what do you call that, the planet which is moving in the elliptical orbit around the sun. That is given by this formula, where A and B are the semi major and semi minor axis respectively. Now if suppose A is equal to B, then what happens to this equation? This equation is going to be E is equal to minus GMM divided by, in place of this A I substitute B itself, this will be 2B, because B plus B is going to be 2B. Now what if this A is equal to B? So in this orbital, if A is equal to B, then you will get a circle. So where this was the semi major axis, sorry, the major axis, and this was the minor axis. If semi major axis is equal to semi minor axis, that case is nothing but the circle only. So what I mean to tell you is, we have earlier derived the formula for the total energy of an object moving in the central force field in circular orbits. The energy of that object in circular orbit in central force field is given by this minus GMM divided by 2 times the r, where r was the radius of that circular path. So here the radius is equal to either A or B, because both are equal. That is what the condition we have taken. So it is very simple that this is the more generalized formula for the energy of an object which is moving in a closed path in central force field. Because if you have this, by substituting the condition for circular orbits, what is the condition for circular orbits? Both this semi major axis and semi minor axis are going to be equal, and then we will get the formula for the energy in circular orbits. Or if they are going to be not equal, and the inequality or the difference between this A and B is going to be bigger, that is going to be more and more elliptical. So that is why this expression E is equal to this GMM divided by A plus B is a more generalized formula for energy of anything, that too especially any celestial object moving in this gravitational force field can be easily get to know. So I hope you understood this concepts of how to write the energy, total energy in elliptical orbits, or the more generalized formula. I hope you understood these concepts. Don't forget to subscribe. Please give thumbs up and click on the bell button to receive all the notifications, and thank you for watching.